Well, I will solve this problem of domain, range, finding inverse, and let's start by finding the domain. The domain of this function is given by the values that make the argument of the square root positive or equal to 0. Let's see. So let's start with 1, and I need that x minus 1 is greater than or equal to 0. This means that x is greater than or equal to 1. So the domain of the function, I will abbreviate dom of f, is made of all x such that, of all x belonging to reals such that x is greater than or equal to 1. So this is the domain of the function. The codomain is given by this set, the set that I circled. So the codomain are all the real numbers. Codomain of f, y such that y belongs to reals. And to find the range, I will start by constructing the graph of f and see. So to construct the graph of f, I will start by, I have two options. One is from the graph of y equals root of x, use the translations and reflections to see how is the final graph, or use a table of values. I will do both for practicing. If I consider the y equals root of x function, I know that this function has the following graph. When x is 0, y is 0. When x is 1, y is 1. And when x is 4, y is 2. So this is the root of x. Now from this, I have x minus 1, root of x minus 1. So it is a translation of 1 unit to the right. So this will be, so when 1, 0, when 2, 1, because 2 minus 1 is 1, root of 1 is 1, and when 5 minus 1, 4, root of 4, 2, so it is 2. So this is y equals root of x minus 1. Finally, the negative sign in front of the root means a reflection on the x-axis. This is the x-axis and this is the y-axis. So a reflection on that axis will be as follows. For 2 will be -1, and for 5 will be -2. So it is here. And this is the function. Yes. So I could leave it like this. It says for x in between 1 and 9, so I should add the value for x equals 9, but I will do for practicing the table of values. If I construct a table of values, maybe it is easier if you don't remember the properties of the translations and reflections. So here I construct a table of values, x, y, and I will give values for the function given, negative root of x minus 1, such that I obtain answers that are integers. So I will start with 1, the minimum value I can use, because remember that here we have that x must be greater than or equal to 1. So the minimum value I can use is 1. Then when x is 2, I will change to the blue pen. When x is 2 and when x is 5. So when 1, 0, when 2 minus 1, 1, root of 1 is 1, negative root of 1 will be negative 1. And when 5 minus 1, 4, root of 4, 2, negative 2. And when 9 minus 1, 8, but root of 8 is not an integer, so I will change, and instead of x in between 1 and 9, I will use x in between 1 and 10. It will be easier. So I like integers as final answers of the image. So negative root of 10 minus 1 is negative 3. Now I can construct again the graph. X and Y. So I have for, I will change the color. For 1, 0, for 2, 1, for 3, 4, 5, 2, this is 2, and then, no, negative 1, negative 2, and for 9, is 5, 6, 7, 8, 9, for 10, not for 9, negative 3. It will be here. I will extend the y-axis so that I have the negative values. So I have negative 1, negative 2, and negative 3. And the function is this one, the graph of the function, the graph of f. So y equals, I could write f of x equals negative root of x minus 1. Clear? So based on this graph, I can say that the image is made of 0 and negative values of y. So here I have all negative values, yes? I'm shading the part of the y-axis where I have images of the function. So the range of f is made of all y's such that y belongs to reals and y is less than or equal to 0. Clear? Once you have the main range and the graph of the function, we have to answer if f is 1-to-1, if it is onto, and justify each answer. So let's see, 1-to-1. So I'm answering now to 1-to-1. And I will say the following. F is 1-to-1, if different elements in the domain have different images. And this is true. For any two different values of x, for any two different values of x that belongs to the domain of the function, this is x1 different from x2, then f of x1 is different from f of x2. And if this happens, we say that the function is one-to-one. So we tick this, the function is one-to-one. Regarding if it is onto, let's see, onto function. What is an onto function? F is onto if each element of the codomain is the image of some element in the domain. This is the range and the codomain coincide. And this is not true because we have that the codomain is made by all the real numbers, the negative reals and the positive reals, but the range is made only of the negative reals, so we don't have images for this part of the set. For this part of the set, we don't have images. So this is not onto. And well, we have to, in 3, answer if it is bijective. It is not bijective because to be bijective, we need that it is one-to-one and onto. If it is, find the inverse, it says. If not, redefine the function such that it is bijective. Then find the inverse of the redefined function. So now I will redefine the function. So as f is not onto, it is not invertible. The idea is to redefine it to find the inverse. To make it onto, what should happen? The range and the codomain must be the same. So for this, we will say the following. I will redefine the function as follows. F will be a new function from set A into set B, such that f of x, the formula is the same, negative root of x minus 1. But A, that is the domain, is still the same. A is the domain of f that we have already found, and B will be a new set. B will be the range of f. So the function now has codomain equal to the range of the function, equal to this set. See, equal to this set, to this one. And now it is as if the positive reals do not exist for the function. And now we can say that the range and codomain are the same. This is each element of the codomain is the image of some element in the domain. This is true now. Now, this function is one-to-one and onto the redefined function, and it has inverse. Yes? Well, now how to find the inverse of the function? To find the inverse, I think that we are in 4. It says, no, we are still in 3. Find the inverse of the redefined function. So to find the inverse of the redefined function, I will write y equals negative root of x minus 1, and I will make x the subject. First, squaring both sides, like this. So we have that y squared. When I square the negative root, we will have x minus 1. Y squared plus 1 will be x. And now this is the inverse. I will change, substitute y by x and x by y. So this is the inverse. The inverse, denoted f to the negative 1, the inverse function is x squared plus 1. Okay? Well, once that I have the inverse, it says, point 4, if the original function was bijective, sketch the inverse on the same pair of axes of f. If not, sketch the redefined function and the inverse of the redefined function together on the same pair of axes. So the graph of the redefined function, f of x equals negative root of x minus 1, is the same as the original. This will be the same graph. So now I will use the same pair of axes to construct here the inverse of the redefined function. So the inverse is y equals x squared plus 1. I will use a table of values. So I will use another color for the redefined inverse, green, for example. X, table of values, y. So here, this is the inverse, yes? And from where will I pick values to construct the graph of the inverse? Well, from the table that I use for the original function. When in the original, when x was 1, y was 0. When x was 2, y was negative 1. And in this way, I will construct the graph of the inverse, but I will use the y value. So when x is 0, I replace in the inverse 0 squared plus 1 is 1. When in the original, when x was 2, y was negative 1. Well, now when x is negative 1, y, negative 1 squared, is 1 plus 1, 2. When negative 2x, in the inverse, negative 2 squared, 4 plus 1, 5. And finally, when x is negative 3, square 8, square 9, sorry, plus 1, 10. Well, these values of the images of the inverse are those that we used for construct are the values of the domain that we picked in the domain of the original function of f to construct the graph of f. And the y values of that are the images of f, we now use to construct the graph of the inverse. Okay? Well, now in the same pair of axes, so I will extend this to at least -3 here, and I will see if I have enough height to construct up to this is 3, 4, 5, 6, 7, 8, 9, and 10 up to here, up to there. So I will extend the y-axis a little bit. I will remove the y, and I will write it there. So now the inverse for 0, I have 1 here. For -1, I have 2. For -2, I have 5. So 2, 3, 3, 4, 5 is here, no? Not in the other mark. Yes, 1, 2, 3, 4, 5. Yeah, it is correct. And for -3, if this is 5, so it will be 6, 7, 8, 9, and 10. Then it's there. I will remove the other marks. And I will improve this. That is wrong. Which is okay. Well, here is 10. Okay. Well, now I will join smoothly the inverse. Okay. So this is the inverse f to the -1 of x equals x squared plus 1. And I see the property that the inverse of f and f have. And this is that it is a reflection on the line y equals to x. Let's construct that line, and you will see here it is. The line y equals to x is the line that passes through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And now if I construct that line, okay, this is the line y equals to x. This function, the inverse, is symmetrical with respect to that line to f. So this is all for this exercise. Hope you have understood. And well, see you then.